Today's talk is joint work with Li, Marius, and also Nick. One of my collaborator, Li Gao, is here in the audience. And you can also feel free to check out our paper on arXiv. Let me start with Lindeblad operators. I'm pretty sure most of you have seen these definitions in the past few days many times. Lindeblad operators are used to describe the Markovian evolution of quantum systems. It is defined like this. So here, H is a Hamiltonian. H is self-adjoint, and then we define it using some like a commutator. V sub j is any matrix of any n by n matrix, and a very simple situation is symmetric semigroup generated by Lindeblad operators. That is to say, we will focus on some Lindeblad operators generated by self-adjoint matrices V sub j, and we don't have this Hamiltonian part. Let's look at a very simple example that is phase damping semigroup. So phase damping semigroup, it is defined via polymatrix sigma 3. And then we can write down the definition L of rho. That is to say V sub j, we only have one V sub j from last page, and also the V sub j is equal to this polymatrix. And then we write down this L of rho, and then we can also calculate what the semigroup looks like. It's kind of interesting because under this semigroup, all the off-diagonal terms will decay exponentially, but the terms on the diagonal will actually remain invariant. Then what will happen when t is really large? So when t is like approaching infinity, the off-diagonal terms will vanish, but the diagonal terms, again, they will remain the same. So every diagonal matrix, it is some equilibrium state because it's not changing under this semigroup. And also we call this semigroup non-primitive because the equilibrium states are not unique. And today I will talk about like the dynamics of all the Markovian evolution. That is to say, I'm interested in what will happen to a quantum state under this kind of like a semigroup. The rough idea is we have a quantum state. Think about like this quantum state here, the higher one is more like a good quantum state. It will slowly decay to the equilibrium state. So there are many questions this is the idea, but I'm also interested in like how fast this will happen or whether this will happen at all. This will happen, and it's gonna happen really fast. So we still need to quantize everything. The first thing is we need to like have some notation for the equilibrium state. From the last slide we have seen, even for a very simple semigroup, the equilibrium state is not unique. Then we need to find like a corresponding equilibrium state for each initial quantum state. And to do that, I'm going to introduce some fixed point algebra. It has kind of a scary name, but it's very simple. We just put all the quantum states invariant under this semigroup into this algebra. And then we can define some conditional expectation from the big matrix algebra to the fixed point algebra. And E of rho, the conditional expectation of this quantum state, it will be the corresponding equilibrium state of rho. And also to study everything, we need something to describe the distance between rho and the equilibrium state. And here we are using relative entropy to describe this kind of distance. And also I know like I'm not writing down the full definition of relative entropy. Part of it is like equal to infinity when under some support condition. But here you don't have to worry about that. We only work with really nice rho and sigma, basically bounded from below and above. For other things, we have some like continuity, some math tools to make it work. And as I said, I'm interested in like the quantum, the state, like the initial state will decay to the equilibrium state like exponentially fast. But what's the meaning of that? That is, the meaning of that is the relative entropy of rho at time t and E of rho and the equilibrium state. This relative entropy, it will decay exponentially at rate lambda. And if every rho, every quantum state satisfies this inequality, I'm going to say the generator or the semigroup satisfies lambda modified logarithmic Sobolev inequality, or you can call it lambda MLSI. The best constant is denoted by alpha sub MLSI of the corresponding operator. So before I annoy you with a bunch of math notations and math formulas, let me tell you the main message of today. Today, as I said, I want to study that MLSI. The first thing is, no matter how annoying, how complicated that inequality is, it's not good enough to study that for quantum systems, for practical purposes. And I will elaborate that later. The short answer is, it's not good enough to study that. So I have to introduce another really long definition. So instead of studying MLSI, the exponential entropy decay of T sub T, we want to have this inequality, this MLSI for T sub T tensor identity operator over matrices of arbitrary size. And this is like not one inequality, it is actually a family of inequalities because we want this to be true for arbitrary n. Since it's kind of complicated, and I think maybe we have to know, is it true for all, like do all Lindeblad operators satisfy this CLSI? Or do some Lindeblad operators at least satisfy this CLSI? This question was answered last year by two groups of people. So by Li Gao and also Kambis. Another group also answered by Li Gao, Marius, Junge, and me. We used different approaches. But this year, today, I will show you a new result, some progress on this problem, because today I'm actually going to present a result. The constant is exponentially better than the constant presented by Li Gao and Kambis last year at QIP. And that's the main message from today. And also, the last question is, can we say something about the decay rate? Because even I claimed like the exponential decay rate is like this year, the decay rate is exponentially better than last year. It's still somehow kind of like abstract. And actually, for some Lindeblad operators, this decay rate is computable, but it is far from like being optimal. And I will not focus on this today. The last question, if you are interested in that, please talk to me after the talk. So then let's do some math. So first is, as I said before, MLSI, it is not good enough for quantum systems. And what I mean by saying that is, we actually want to have some tensorization stability. That is to say, if we have a quantum system here and we have some like it satisfies MLSI, and I have another quantum system here, say the environment, maybe it also satisfies some MLSI. Sorry. So if I tensor them together, do they at least satisfy like a MLSI with the smaller decay rate? So this question, so for classical case, like for classical Markov semigroup, it is true, and this is like very simple to prove. But this is not true for Lindeblad operators. And that's why I need to introduce this complete version, the complete modified logarithmic Sobolev inequality. So, I mean, that's why we have to study this family of inequalities. And so Mike Brennan, Li Gao, and Marius Junge, they also gave like an example showing that the CLSI constant is actually strictly strictly smaller than MLSI constant. That's why, that's the example where the two constants actually differ. And I think the L is the depolarizing, the generator of depolarizing semigroup. So if we work with this complete version, we actually have this tensorization stability. Then we can tensor two quantum systems together, and we can still say something about the CLSI constant of the whole system. And that's why, that's why we have this complete order in our title. Is because even it's kind of more complicated, but it can give us some really good properties. And then I can so now I can talk about the main theorem of today. As I said, we got some exponentially better constant, and actually the main result, it was then using some framework of quantum Markov semigroup. If you are not familiar with this, you can just consider this T sub T as still as the semigroup generated by the Lindeblad operator, and this M you can consider that as still the matrix. But here M can be a finite van Neumann algebra with a nice trace. So the framework can be actually generalized. And actually, this will work for GNS symmetric, but here I'm just going to use trace symmetric to simplify things. And as you can see from the title, the CLSI constant, it is lower bounded by 1/2 CB return time. Then what is, so a finite CB return time will imply CLSI. Then what is CB return time? So here is the definition, but roughly speaking, CB return time, it is the infimum time t such that the semigroup is very close to the conditional expectation. By saying very close, I'm just saying close enough, 1/10. And here, this is a vector space. If we consider primitive, that is to say there is only one unique equilibrium state, this vector space will actually become L1 space, L1 of M. And so the main result depends on a improved data processing inequality. Before I mention anything any condition, let's look at the conclusion first. So if the coefficient on the right-hand side is 1, then this is just the data processing inequality, because phi here I'm going to assume is a quantum channel. So, but if we assume more conditions on this phi, on this quantum channel, we can get this stronger data processing inequality. And this K sub CB, it is more like a discrete version of the CB return time I introduced on the last slide. Next, I want to prove the main result using this key theorem. It's actually quite short. First, I need to introduce another or equivalent formulation of MLSI. MLSI can actually be formulated as, it is actually equivalent to this. I sub A of rho, this is the quantum Fisher information. It is defined as trace A of rho log rho. And there is a very important identity that connects quantum Fisher information and relative entropy. I think it's called quantum de Bruijn lemma. It says Fisher information is the negative derivative of relative entropy. And first, we are going to let T sub M be the CB return time divided by 2M. And then this is a application of the key result I showed from last year, the improved data processing inequality. With this inequality and the quantum de Bruijn lemma, that is to say, Fisher information, the first line, is actually the negative derivative of relative entropy. So first we use that, and then the second step, instead of letting t goes to 0, we let m goes to infinity. Basically, just rewrite t as CB return time divided by 2m. And the next step, we just use the improved data processing inequality. And then we get MLSI. Or if you consider everything is CB in the CB sense, like a complete sense, then we can get CLSI. So once we have the improved data processing inequality, the main result is very simple. But this is still like a kind of far from what I claimed, the constant, because here I only showed something about return time. Then what is the return time? How do we find out the return time for some quantum, for some operators, for some semigroups? And so this is what we have done first to bound CB return time. And actually today, I'm only going to mention the last situation, that is to say, with this extra dimension constant. So roughly speaking, the CB return time, if we have this, I will introduce this later, but let's pretend you know what this is. So it's called this dimension constant. If this dimension constant is finite, and if we also have some Poincare inequality, that's like the spectral gap. If we have those, and we have another like inequality like this, then we have the CB return time. The CB return time is bounded like that. So I think now at this point, I need to introduce what is this dimension constant. Unfortunately, I have a typo in here. In the definition of the dimension constant, and this is the correction. I forgot to put C here. Basically, you need to put C here. So what's the meaning of this? So the meaning of this C of E, it is like a constant related to the structure of the fixed point algebra. For example, if my fixed point algebra, if my equilibrium state is unique, it's just like 1 over d, 1 over d, 1 over d, the normalized identity matrix, then this C of E, it is actually equal to the dimension of the matrix. And then this CB version, basically, again, we needed to consider the conditional expectation tensor identity, but you have seen this because we always want to study everything in the complete order. So again, for the primitive case, this CB constant will be upper bounded by n squared. That's the dimension of the matrix. And with this result, I can finally just, with the bound for CB return time, we can get the lower bound of CLSI constant for Lindblad operators. It is like this. So first I want to say this result or everything I've mentioned today, it remains true for GNS symmetry. And please feel free to check out the paper. So next thing is, last year what Liga and Cambis, they proved is such a result. So the constant they give, it also depends on the spectral gap. But if you look at it also depends on the dimension constant. But here they are using the dimension constant itself. But now we can improve it and we can use the logarithmic, the log of the dimension constant. And again, last year we also gave another like a lower bound for this Lindblad operator using geometric constant. The problem is I cannot, or at least I cannot compare whether which constant is better because they are just like from really different perspectives. So one more thing. I think that's it. It's kind of fast.
Thank you for the presentation. So we got time for some questions. Sorry.
So thank you for the interesting talk. So my question is that, so the similar to the relation between complete positivity and K positivity, in your study such a K hierarchy is emerged?
Sorry, can you repeat the question? I don't quite follow you.
Do you know K positivity? K positivity means a positive for any tensor product of dimension smaller than K identity. So in your study, complete. So in this study, so
complete. You mean the before the complete definition?
yes, complete. In your complete definition can be changed. The tensor product is the identity less than K. In such definition, so in about completely positive map, such a K positivity is also important sometimes. So in your study, such a K definition is important or not so important?
So you mean, can I replace this identity operator by another operator?
Yeah.
Actually, that's an interesting question. At this point, I don't think we have any result, but I remember last year I had like a conversation with Chao Mei, and we didn't get anything. But like, I'm gonna say, this is just like my feeling. If you want to study for any K, like any other operator, maybe it's kind of hard. But if you want to study some, like, I think you need to really like choose.
Yeah.
So do you? So in this definition, you define the sum only one operator Mn,
Yes.
or some of the set of M, the sequence of Mn.
I get it. We study it for arbitrary Mn. So, for example, you can you can do it T sub T tensor like you can do it for 2 by 2, and that's for M2. And if you do it for 3 by 3, that's M3. So the definition is we want it to be true for 2, 3, for everything. So it's a family of inequality. Yes, for
Right.
all of n's. And actually, you can.
Okay. I give you the mic back, but maybe we can come to an end also.
Okay.
Sorry. So in my definition is so when you assume the not any n, so but sufficiently large n, only sufficiently large k, you assume so in your definition. So in this,
So
how
you
about
want
in
to
such a
study
definition?
it only for some k? I'm gonna say like so I'm gonna say my experience is for k. Are you trying to like sort of like reduce the difficulty of this problem for some k? My impression is it looks simpler, and in theory, if you study the ML as a constant of T sub T tensor MK, this should be smaller than alpha CLSI of T sub T. But actually, the studying of this question itself, it is not like much simpler, because we got many counter examples or many counter examples by just letting k equals 2. So it's not like just studying finite situations will make things easier. But maybe if you like specify the semi-group, maybe for some special cases we have some.
Thanks. Maybe we can move on, and maybe there's another question. Yeah.
Hi, thank you for the nice talk. I was wondering because I assume that in your settings, your Lindblad operators are time independent, yes? Are there any techniques, do you know anything about similar kind of reasonings towards situation when the Lindblad operator could be time dependent?
So you want to study like time-dependent Lindblad operator, and I think I can actually say something about it. So there is a paper by Marius Junge and Peixue Wu. They studied like perturbations of the generators. I think that's related, but you also have to make sure it doesn't change like how do I say that fast or dramatically. Yeah.
Okay, thank you. So yeah, let's thank Jane Hao again.